In our next section, we're going to look at virtual port channels on NXOS and first talk about just some of the background information about how the multi-chassis link aggregation, or the MLAG, works in general, and then specifically how it's implemented with the vPC. Once we go through the basic implementation and show just the generic steps, the generic workflow of how to run the vPC, then we'll start to get into more details of what are the problem designs that you can run into, and then what are the different advanced features and functionality of the virtual port channel. Now, as we talked about previously with our classical Ethernet design, and we're looking at our three-tier design with the access, distribution / aggregation, and the core layers, one of the problems that we run into down at the access layer is that typically this is going to be a single point of failure for both the links and the nodes. So it means that when we look at our physical attachment from the access switch down to the end servers, traditionally we're only using one physical port, which means if the physical switch goes down or the physical link goes down, then the end host is going to be isolated from connectivity. Now again, from an enterprise point of view, if this is your desktop, maybe that's not an issue. You could swap out the cable, swap out the NIC card. But assuming we're talking about data center in a high availability environment, then we don't want to, or we want is to try as much as possible to eliminate single points of failure, like redundant power supplies, redundant NIC cards, redundant physical links, redundant switches, and so on and so forth. But the problem we would run into in addition to this is that as you start to throw more cards, more links, more switches at the problem, layer 2 multipath from a spanning tree point of view isn't supported. So if we were to buy multiple NIC cards, multiple switches, so on and so forth, essentially that's going to be just a waste in terms of CapEx, because those boxes are going to be sitting there from a spanning tree point of view just waiting for the failure to occur. Okay, so what are the ways that we can get around this problem then? Okay, so how can we fix the high availability requirements of the access node? Okay, one is to add the additional link and node redundancy. But at the same time, how do we avoid having wasted links that are sitting there doing nothing? The way that we're going to do this is basically to trick the end host into load balancing the traffic between multiple physical switches as opposed to just sending traffic to one physical box. Now, the first problem here, how do we improve the redundancy requirements? This is going to be fairly self-explanatory. Okay, the way we do this is just by adding dual uplinks. So in today's networks, 10 gig Ethernet is commodity, 40 gig Ethernet is available as cards down to the access layer. Okay, future 100 gig, and then kind of speeds in between there, 25, 50 gig, etc. are currently in standardization. The problem, though, is that the redundancy doesn't necessarily address the multipath problem. That just because I have 2 by 10 gig links from the access layer northbound doesn't mean that the server is going to actually be able to load balance the traffic in multiple directions. Now, we'll see that there are some solutions to take this away from a network problem and to push it down to the OS and basically make it up to the application in order to decide how the traffic is going to be distributed. So, for example, we could have a virtual switch within the scope of a hypervisor do the forwarding decision based on the source MAC address of the virtual machine or the source virtual port identifier of the vSwitch, and basically say from the network point of view, you don't know that the end host is load balancing. You're just going to see one MAC address going one way, one MAC address going the other way, but you're not going to be able to load balance per flow. So if I have 2 transfers that are going to the same web server or the same file server, from a layer 2 switching point of view, we're going to always follow the same physical path down to the access node. So assuming that we don't want to let this be up to the OS, and assuming that we do want to load balance per flow, one of the ways that we can solve this is by implementing a multi-chassis link aggregation, or an MLAG, between the access switches and the downstream access device. So the end resulting logic of this is that the multi-chassis lag is going to act as if it was a single lag from the end host point of view. Okay, so a port channel, NIC team, etc., whatever the naming convention is, the end host is going to be able to use whatever load balancing method is built into the upper level drivers, okay, like the Intel NIC drivers, the Cisco drivers, etc. or it could be some sort of additional software layer like we'll see in the Nexus 1000V when we're talking about the distributed virtual switch in ESXi or the other virtual switches like in Hyper-V KVM, where when we look at this from a physical connectivity point of view, we're now going to have our downstream node, which would be the server, and the server is going to be connected to access switch 1 and to access switch 2. So we have multiple physical links. And then somehow behind the scenes, access switch 1 and 2 are going to be synchronizing the control plane between the two of them. And from the server's point of view, we're just going to have a single logical port channel where we would put our IPv4 or IPv6 address onto that logical team interface. So basically, from the server's point of view, they're going to think that they have multiple physical links going to the same upstream box. But we're going to need to do some magic on the back end of these upstream access switches in order to spoof this information down to the end node. So in the previous original design that we saw, the port channeling was only going to be between two point-to-point connected devices. Okay, so one upstream box, one downstream box. So for example, we have an access catalyst switch that has multiple physical links that we're channeling together. End result of this is that we're going to increase the bandwidth as an aggregate, but we're not necessarily getting rid of this single point of failure problem. So we might have two fast Ethernet links going to fast Ethernet switch, but if that switch goes down, then the end result is that the node is going to be isolated. Okay, so by trying to solve both at the same time, we're going to have the network wired as a physical triangle. So we're going to have 3 boxes as opposed to 2. We're going to have one downstream device and then 2 upstream devices. So for example, the in-host is going to be multi-home to 2 Catalyst 3750s via 2 gig links, and then logically this is going to form a 2 gig port channel. So we're increasing the bandwidth and we're increasing the resiliency, because if one of the links goes down or one of the upstream access switches goes down, the in-host is going to be able to heal the traffic forwarding around this failure.